The JCO uranium conversion facility in Tokaimura represented a particular philosophy of nuclear criticality control that would prove fundamentally flawed. Licensed in November 1980 and modified in 1984 to process enriched uranium solutions up to 20% U-235, the facility embodied the regulatory assumption that administrative controls could reliably prevent criticality accidents without requiring engineered physical safeguards or specialized monitoring systems. This assumption would shape every aspect of the facility's design, operation, and oversight until September 30, 1999. The facility's core process involved converting uranium oxide powder into uranyl nitrate solution for use in research reactors. The government-approved procedure specified a three-stage process designed around criticality prevention through geometric control and mass limitation. Uranium powder was first dissolved in a dissolution tank, then transferred to a buffer column for homogenization and mass control, before final processing in a precipitation tank surrounded by cooling jackets. This sequence reflected a fundamental design principle. The buffer column provided absolute criticality safety through its geometry, while subsequent operations relied on administrative controls to maintain safe conditions. The buffer column represented the system's primary engineered safeguard. Its cylindrical geometry with a diameter designed for criticality safety meant that nuclear chain reactions were physically impossible, regardless of uranium concentration, total mass, or operator actions. This geometric constraint provided what nuclear engineers term always safe conditions protection that could not be defeated by human error, equipment failure, or procedural violations. The buffer column's criticality-safe geometry represented proven engineering practice dating to the earliest fuel processing facilities. The precipitation tank operated under entirely different safety principles. With an internal diameter of approximately 450 millimeters and cylindrical configuration, this vessel could theoretically support a sustained nuclear chain reaction if sufficient enriched uranium accumulated under appropriate moderation and reflection conditions. The approved safety controls for this tank relied exclusively on administrative measures, limiting individual batch sizes to 2.4 kilograms uranium, maintaining uranium concentrations below 380 GUL, and ensuring that only single batches were processed at any time. This two-tier safety philosophy created a critical interface where absolute physical protection transitioned to procedural protection. The design assumed that operators would invariably use the buffer column for homogenization and mass control before transferring controlled quantities to the precipitation tank. This assumption was not enforced through interlocks, procedural constraints, or monitoring systems. It was simply expected that trained personnel would follow approved procedures because those procedures had been established as mandatory. The facility's training program reflected this administrative control philosophy by emphasizing procedural compliance rather than understanding of criticality physics. Workers received instruction on the approved process steps but limited education about the physical principles underlying those steps. Training focused on what to do rather than why specific actions were required or what consequences might result from deviations. This approach was consistent with the regulatory framework's assumption that operators did not need to understand nuclear physics because proper procedures would prevent hazardous conditions from developing. The regulatory licensing process had explicitly concluded that criticality accidents were not credible at the JCO facility given its approved procedures and administrative controls. This determination eliminated requirements for criticality accident alarm systems, specialized emergency planning, and enhanced training in criticality recognition and response. The licensing analysis assumed that the combination of geometric safeguards in the buffer column and administrative controls in subsequent operations provided adequate protection against criticality events. This not credible determination reflected broader regulatory confidence in administrative control systems for nuclear operations. The Japanese regulatory framework assumed that properly trained personnel operating under approved procedures could reliably prevent criticality accidents through procedural compliance alone. This assumption was based on successful experience with similar facilities and confidence in Japanese manufacturing quality control practices. The absence of criticality monitoring equipment, represented a logical extension of the not credible determination. If administrative controls prevented criticality accidents, then systems to detect ongoing nuclear chain reactions served no safety function. The facility's radiation monitoring focused on detecting normal operational radiation levels and potential contamination rather than monitoring for neutron radiation or other indicators of nuclear fission reactions. Economic pressures within the nuclear fuel processing industry created systematic incentives that conflicted with conservative safety practices. JCO operated in an increasingly competitive international market, where efficiency and cost control determined commercial survival. The approved procedures, while providing safety margins, were also time-consuming and labor-intensive compared to simplified alternatives that workers might develop through experience and innovation. The facility's quality assurance program measured compliance with documented procedures rather than maintenance of safety margins or achievement of safety objectives. This approach was consistent with standard manufacturing practice, where process consistency generally correlates with product quality and operational safety. However, it also meant that quality assurance could not detect situations where consistent implementation of procedures was systematically reducing safety margins. The organizational structure reflected confidence in administrative controls through the assignment of multiple safety responsibilities to individual personnel. The same manager served as both safety control manager and quality control manager, reflecting the assumption that these functions were complementary rather than potentially conflicting. This consolidation was economically efficient, but eliminated independent safety oversight that might have detected conflicts between operational optimization and safety maintenance. Training for infrequently performed operations relied on workers' general understanding of facility procedures rather than specific instruction in the unique requirements for different materials or processes. The facility processed primarily low-enriched uranium, 3-5% U-235, with only occasional campaigns for intermediate, enriched material, 18.8% U-235. Training programs did not emphasize the different criticality safety requirements for these different enrichment levels, assuming that workers who could safely handle low-enriched material could adapt their procedures for intermediate enriched material. The procedural modification process reflected organizational confidence that operational improvements would inherently maintain safety. Workers were encouraged to identify inefficiencies and develop improved procedures, with management approval typically focused on operational benefits rather than safety implications. This process assumed that workers' practical experience provided adequate basis for evaluating procedural modifications, supplemented by management review that could identify any safety concerns. The facility's economic environment created systematic pressure for procedural optimization that complemented the Kaizen culture of continuous improvement. Reduced staffing levels increased workload pressures, while international competition demanded cost reductions and efficiency improvements. These pressures were not inherently incompatible with safety, but they created organizational incentives that favored procedures perceived as unnecessarily conservative or inefficient. The interface between the buffer column's absolute safety and the precipitation tank's administrative safety created the fundamental vulnerability that would enable the eventual accident. This interface assumed perfect procedural compliance and complete understanding of why the approved process sequence was mandatory. Neither assumption proved sustainable under operational pressures and organizational evolution over time. The design philosophy embodied in the JCO facility represented the intersection of engineering confidence, regulatory assumptions, and organizational culture that characterized nuclear fuel processing in the 1980s and 1990s. Administrative controls were perceived as reliable, procedural compliance was assumed to be sustainable, and workers were expected to maintain competence and follow procedures indefinitely without requiring deep understanding of underlying physical principles. The systematic erosion of criticality safety margins at JCO began years before the September 1999 accident, through a series of procedural modifications that appeared individually reasonable but cumulatively undermined the facility's safety philosophy. The most significant of these changes occurred in 1996 when workers modified the uranium dissolution process to use portable stainless steel buckets rather than the approved dissolution tank. This modification established both the precedent and mechanism for bypassing engineered safeguards while maintaining organizational confidence in operational safety. The 1996 procedural modification emerged from workers' practical experience with the approved dissolution process. The original procedure required dissolving uranium oxide powder in a fixed dissolution tank before transferring the solution to the buffer column for homogenization. Workers identified this process as inefficient because it required additional equipment setup, monitoring, and cleaning between batches. The dissolution tank also created potential bottlenecks when multiple batches needed processing within tight production schedules. Workers developed an alternative approach using 10-liter stainless steel buckets for uranium dissolution. This modification eliminated several procedural steps, reduced processing time, and provided greater flexibility for batch scheduling. The bucket dissolution could be performed at convenient locations, required less equipment preparation, and simplified material handling between process steps. From an operational efficiency perspective, the modification represented a clear improvement over the approved procedure. The organizational response to this modification reflected the facility's confidence in worker judgment and procedural adaptation. The modification was implemented in practice and demonstrated to be effective before seeking formal approval. This sequence reversed the normal relationship between procedure approval and operational implementation, creating a framework where operational validation preceded safety evaluation rather than following it. Management review of the bucket dissolution modification focused primarily on its operational benefits and demonstrated effectiveness. The Manufacturing and Quality Assurance divisions approved the change based on successful operational experience and efficiency improvements. However, the Safety Management Division was not included in this approval process, creating a critical gap in safety oversight. This exclusion reflected organizational assumptions that operational improvements were inherently compatible with safety objectives. The formal approval of the 1996 modification established several important precedents that would influence future procedural changes. First, it demonstrated that workers could successfully identify and implement process improvements based on practical experience. Second, it showed that management would approve modifications that provided clear operational benefits. Third, it created confidence that the facility's administrative control framework could accommodate procedural flexibility without compromising safety. The approved modification also created new operational capabilities that had not been anticipated in the original facility design. Dissolving uranium in portable buckets rather than fixed tanks enabled more flexible material handling approaches. Workers could combine dissolved uranium from multiple batches, transport solution more easily between process areas, and adapt dissolution procedures to accommodate varying uranium feed materials or production requirements. Training programs were updated to reflect the approved modification, but did not adequately address its safety implications or the constraints that should govern its application. Workers learned the new dissolution procedure, but received limited education about why the original procedure had been designed differently, or what safety considerations should limit the application of bucket dissolution. Training emphasized procedural compliance with the revised steps, rather than understanding of the underlying safety principles that the original procedure had been designed to protect. The facility's quality assurance program adapted to measure compliance with the revised procedures without systematically evaluating whether those procedures maintained adequate safety margins. Quality metrics focused on consistency of implementation rather than achievement of safety objectives. Workers who effectively implemented the bucket dissolution procedure were evaluated positively for their procedural compliance, regardless of whether their specific implementation maintained appropriate criticality safety controls. Supervisory oversight evolved to accommodate the modified procedures without independent evaluation of their safety adequacy. Supervisors learned to monitor worker performance against the revised procedures and to evaluate effectiveness based on operational results rather than safety margin maintenance. This adaptation was natural and necessary for effective supervision, but it also meant that supervisory oversight became focused on ensuring effective implementation of modifications rather than ensuring that modifications remained safe. The regulatory interface with the modified procedures revealed important limitations in oversight effectiveness. The 1996 modification was eventually documented and submitted to regulatory authorities, who reviewed it for compliance with license conditions rather than conducting independent safety evaluation. This review process assumed that facility management was responsible for ensuring that procedural modifications maintained safety, while regulatory oversight verified that documented procedures matched operational practice. The success of the 1996 modification created organizational momentum for additional procedural improvements. The demonstrated benefits of worker-initiated modifications established expectations that further improvements were possible and desirable. The facility's Kaizen culture, emphasizing continuous improvement, provided both motivation and organizational support for identifying additional inefficiencies and developing solutions. Economic pressures reinforced these trends by creating systematic incentives for procedural optimization. JCHO's financial situation had deteriorated significantly during the 1990s due to international competition in uranium processing markets. Company revenues declined from 3.25 billion yen in 1991 to 1.72 billion yen in 1998, forcing repeated cost reduction initiatives. Personnel reductions were particularly severe among technical staff, declining from 34 to 20 workers during this period. The staffing reductions created multiple cascading effects that compromised safety oversight capabilities. Fewer technical personnel meant that individual workers carried broader responsibilities, including concurrent assignments in functions that had previously been separated. The safety control manager also served as quality control manager, eliminating independent safety oversight of operational decisions. The safety committee lost jurisdiction over accident investigation, reducing organizational focus on safety-significant events and trends. Personnel reductions also eliminated much of the facility's specialized criticality safety expertise. The remaining technical staff had broad responsibilities across multiple facility functions rather than deep expertise in specific safety disciplines. This knowledge reduction meant that the facility's capability to evaluate the safety implications of procedural modifications was significantly compromised precisely when economic pressures were creating incentives for such modifications. The organizational culture adapted to these resource constraints by emphasizing operational flexibility and worker initiative. Management encouraged workers to identify problems and develop solutions rather than relying on extensive technical support or formal analysis. This approach was economically necessary given staffing limitations, but it also placed greater responsibility on workers to evaluate safety implications of their procedural adaptations. The facility's training program reflected these organizational changes by focusing on procedural compliance rather than technical understanding. With reduced technical staff and economic pressures for efficiency, training emphasized what workers needed to do rather than why specific procedures were required or what physical principles they protected. This approach maintained operational capability while reducing the knowledge base necessary for workers to evaluate when procedural modifications might compromise safety. Quality assurance systems evolved to measure procedural consistency rather than safety effectiveness under these resource constraints. With limited technical staff available for comprehensive safety evaluations, quality assurance focused on metrics that could be measured efficiently, compliance with documented procedures, consistency of implementation, and achievement of operational objectives. This approach could detect procedural violations, but could not evaluate whether compliant implementation maintained adequate safety margins. The cumulative effect of these organizational changes was to create systematic bias toward procedural modifications that improved operational efficiency while gradually reducing safety margins. The knowledge necessary to recognize these safety reductions was systematically eliminated through personnel cuts. The oversight mechanisms capable of detecting safety margin erosion were eliminated through organizational consolidation. The cultural incentives favored operational improvements that might inadvertently compromise safety. The 1996 modification represented not just a procedural change but a fundamental shift in the facility's approach to safety management. The original safety philosophy assumed that approved procedures would be followed as written, with modifications requiring comprehensive safety evaluation before implementation. The revised approach assumed that operationally successful modifications were inherently safe, with safety evaluation occurring after implementation based on operational experience rather than analytical assessment. This shift created the organizational framework within which further modifications would be evaluated and implemented. Future procedural changes would be assessed primarily based on their operational benefits and demonstrated effectiveness, rather than their impact on safety margins. The mechanisms for detecting safety margin erosion were systematically weakened precisely when economic pressures were creating incentives for further optimization. The production order for Joyo fast breeder reactor fuel in late September 1999 introduced operational requirements that would expose every weakness in JCO's modified safety framework. The fuel specification called for uranol nitrate solution enriched to 18.8% U-235, an intermediate enrichment level that created fundamentally different criticality safety requirements than the 3-5% low-enriched uranium typically processed at the facility. This material property change occurred within an organizational context where specialized knowledge had been systematically reduced and procedural modifications had been normalized without comprehensive safety evaluation. The Joyo fuel production represented an infrequent but routine part of JCO's business portfolio. The facility had previously produced similar intermediate enriched fuel approximately every 3 years, with the last campaign occurring in 1996. During the intervening period, the facility had focused primarily on low-enriched uranium processing, while experiencing significant personnel reductions that eliminated much of its specialized criticality safety expertise. The combination of infrequent operations and reduced technical staffing created conditions where institutional knowledge about intermediate enrichment requirements was effectively lost. The 3 workers assigned to the Joyo production, designated as a special crew due to their assignment to specialized operations, had varying levels of relevant experience. The supervisor had participated in previous intermediate enriched campaigns but had not worked with this material for several years. The 2 operators had extensive experience with routine low-enriched uranium processing but no specific training or experience with intermediate enriched material. This combination of outdated experience and limited specialized knowledge created the fundamental human factors vulnerability that would enable the accident sequence. The facility's approach to restarting infrequently used processes reflected confidence in procedural documentation and worker adaptability rather than systematic safety review. No formal restart authorization process was required for the Joyo production. No safety analysis was conducted to verify that existing procedures remained adequate for intermediate enriched material. No refresher training was provided to ensure that workers understood the specific criticality safety requirements for 18.8% enriched uranium. Management assumed that workers competent to handle low-enriched uranium could safely adapt their procedures for intermediate enriched material. This assumption reflected a fundamental misunderstanding of how enrichment levels affect criticality safety parameters. The critical mass for uranium decreases dramatically as enrichment increases, with 18.8% enriched uranium requiring much smaller quantities to achieve criticality than the 3-5% material routinely processed. The geometry requirements, concentration limits, and mass controls that provided adequate safety margins for low-enriched uranium were insufficient for intermediate enriched material. These physical differences were not reflected in worker training or procedural documentation. The production sequence began on September 29 with dissolution of uranium oxide powder using the bucket dissolution procedure approved in 1996. Workers dissolved approximately 2.4 kilograms of 18.8% enriched uranium in each 10-liter stainless steel bucket, creating solutions with concentrations below the 380 Joule limit specified in facility licensing documentation. Each batch represented material within approved individual limits, but the cumulative handling of multiple batches would create conditions not anticipated in safety evaluations. The workers' decision-making process reflected their operational experience and understanding of facility procedures rather than specific knowledge of intermediate enrichment requirements. They planned to use the precipitation tank for homogenization rather than the approved buffer column, based on their experience that this approach was more convenient and had been used successfully in previous campaigns. This decision eliminated the facility's primary engineered safeguard against criticality without conscious recognition of its safety significance. The rationale for bypassing the buffer column reflected practical operational considerations that seemed reasonable based on workers' experience with low-enriched material. The buffer column was perceived as inconvenient for mixing and homogenization operations due to its geometry and access limitations. The precipitation tank offered more working space, easier access for mechanical stirring, and better visibility for monitoring homogenization progress. Workers had successfully used similar approaches with low-enriched uranium without adverse consequences. The workers also believed they were following established precedent from previous intermediate-enriched campaigns. According to their recollection, in 1995 and 1996 campaigns, similar quantities of uranium, approximately 16 kilograms, had been processed in the buffer tank for mixing and homogenization. They extrapolated from this experience, reasoning that if this quantity could be safely handled in one vessel, it could be safely handled in another vessel of similar size. This reasoning was logical within their understanding of facility operations, but ignored critical differences in vessel geometry and criticality safety characteristics. Before implementing their planned approach, the workers consulted with facility management about the safety of performing homogenization in the precipitation tank rather than the buffer column. They asked a technical expert whether mechanical stirring could be safely performed in the precipitation tank for their production campaign. The expert approved this approach, apparently believing that the workers were planning to process low-enriched uranium rather than intermediate-enriched material. This management consultation represented the final potential barrier to the unsafe procedure, but it failed due to miscommunication about material specifications. The technical expert consulted by the workers was responsible for multiple facility functions and did not have immediate access to detailed specifications for the Joyo production. The consultation occurred as a brief conversation rather than formal safety review, with no documentation of the technical basis for approval. The expert's response was based on general familiarity with facility operations rather than specific analysis of intermediate enrichment requirements. The approval process reflected the facility's degraded technical oversight capability following personnel reductions and organizational changes. The expert providing approval had broad responsibilities across multiple facility functions rather than specialized focus on criticality safety. No systematic process existed for ensuring that technical approvals were based on complete and accurate information about material, specifications, operational parameters, and safety requirements. The consultation process relied on informal communication and general expertise rather than documented analysis. On September 30th, workers continued the production sequence by transferring dissolved uranium solutions to the precipitation tank using the bucket dissolution procedure. They poured solution directly from stainless steel buckets into the precipitation tank through a funnel, accumulating multiple batches in a single vessel. Each individual transfer involved quantities within approved single-batch limits, but the accumulation process violated the fundamental premise of the facility's criticality control strategy. The workers' mental model of the operation reflected their training and experience with low-enriched uranium rather than understanding of intermediate enrichment physics. They understood the 2.4 kilograms batch limit as applying to individual transfers rather than total accumulation. They viewed the precipitation tank as a suitable vessel for uranium processing based on their experience with other operations. They interpreted the concentration limit as controlling criticality risk, without understanding how geometry and total mass affected critical assembly formation. The gap between worker understanding and physical reality widened with each batch transfer. The workers believed they were implementing approved procedures for routine uranium processing, while the physical system was approaching conditions that could support sustained nuclear chain reactions. The administrative control framework assumed that workers would recognize and avoid dangerous configurations, but the workers lacked the knowledge necessary to make such recognitions. The accumulation logic reflected reasonable extrapolation from approved procedures combined with incomplete understanding of criticality physics. Workers knew that individual batches were safe, that concentration limits were maintained, and that similar operations had been performed previously. They did not understand that criticality safety depends on the interaction of multiple parameters, including total mass, geometry, moderation, and reflection. and that safe individual components could combine to create unsafe total configurations. The facility's administrative control philosophy created conditions where logical decisions based on incomplete information could systematically approach physical limits. The workers' actions throughout September 29 and 30 were rational within their understanding of facility requirements and safety constraints. They followed procedures they believed were approved, consulted with management when uncertain, and implemented approaches that had proven successful in their experience. The fundamental problem was not worker error, but the systematic erosion of the knowledge base necessary to recognize when procedural adaptations approached physical safety limits. The facility's confidence in administrative controls had eliminated the monitoring systems that might have detected dangerous conditions. The personnel reductions had eliminated the expertise that might have recognized the safety implications of procedural modifications. The training philosophy had emphasized compliance rather than understanding, leaving workers unable to evaluate the safety adequacy of their own actions. By the morning of September 30th, conditions were aligned for a criticality accident that would be both devastating and inevitable. Workers were implementing procedures they believed were safe and approved. Management had provided approval for what they understood to be routine operations. The facility's safety systems were functioning as designed within the administrative control framework. Yet physical reality was approaching thresholds that would overwhelm all administrative protections once critical mass accumulation exceeded geometric constraints. At approximately 10:35 a.m. on September 30, 1999, the workers completed their 7th transfer of uranyl nitrate solution into the precipitation tank, bringing the total uranium content to approximately 16.6 kilograms of 18.8% enriched material in roughly 40 liters of solution. This accumulation exceeded the critical mass threshold for the vessel geometry and uranium concentration, initiating a nuclear chain reaction that would continue for 20 hours and demonstrate the absolute primacy of physics over administrative controls. The criticality event marked the moment when theoretical safety margins collapsed into physical reality, revealing how administrative control systems could enable the very events they were designed to prevent. The precipitation tank geometry provided conditions conducive to criticality once sufficient enriched uranium accumulated. With an internal diameter of approximately 450 millimeters in cylindrical configuration, the tank lacked the neutron leakage characteristics necessary to prevent chain reactions at higher uranium concentrations. Unlike the criticality-safe buffer column, which was designed to prevent chain reactions regardless of material loading, the precipitation tank could support sustained nuclear fission if sufficient fissile material accumulated under appropriate moderation and reflection conditions. The physical parameters governing criticality reflected fundamental nuclear physics principles that operated independently of facility procedures or worker intentions. Critical mass depends on fissile isotope concentration, material geometry, neutron moderation, neutron reflection, and the physical arrangement of materials within the system. The JCO precipitation tank provided optimal conditions across all these parameters once sufficient 18.8% enriched uranium accumulated in aqueous solution. The uranium enrichment level of 18.8% U-235 provided sufficient fissile content to sustain chain reactions at uranium concentrations well below facility administrative limits. Natural uranium contains only 0.7% U-235, requiring extensive concentration or optimal geometry to achieve criticality. The 18.8% enrichment reduced critical mass requirements by more than an order of magnitude compared to natural uranium, making criticality achievable at masses and concentrations that seemed conservative based on experience with low-enriched material. Water in the uranyl nitrate solution provided near-optimal neutron moderation for the accumulated uranium. Neutron moderation slows neutrons from fission reactions, increasing their probability of causing additional fissions rather than escaping the system. The hydrogen in water molecules is particularly effective at slowing neutrons to thermal energies where fission cross-sections for U-235 are maximized. The solution chemistry provided moderation conditions that significantly reduced critical mass compared to dry uranium compounds. The stainless steel construction of the precipitation tank and surrounding cooling jackets provided neutron reflection that further reduced critical mass requirements. Neutron reflectors reduce neutron leakage from fissile systems by scattering escaping neutrons back into the active region. The tank walls, cooling water, and nearby equipment all contributed to neutron reflection, effectively increasing the neutron multiplication factor for the accumulated uranium solution. The combination of these physical parameters, high enrichment, aqueous moderation, reflective geometry, and concentrated fissile material created conditions where criticality became inevitable once total uranium mass exceeded the threshold value. This threshold was determined by nuclear physics rather than administrative controls, and no amount of procedural compliance could prevent chain reactions once critical conditions were achieved. The criticality event began with a prompt critical excursion that released intense bursts of neutron and gamma radiation. During prompt criticality, the neutron multiplication rate exceeds the delayed neutron fraction, causing rapid exponential increases in fission rate limited only by physical feedback mechanisms. This initial pulse generated sufficient energy to create localized heating, steam formation, and convective mixing within the uranyl nitrate solution while producing radiation levels that immediately triggered area monitoring systems throughout the facility. The intense radiation pulse during prompt criticality created radiation fields that posed immediate life-threatening hazards to personnel in the vicinity. Gamma radiation and neutron radiation from fission reactions reached levels orders of magnitude above normal facility background, with dose rates sufficient to cause acute radiation syndrome within minutes of exposure. The 3 workers closest to the precipitation tank received estimated doses of 16 to 20 Gray equivalent, 6 to 10 Gray equivalent, and 1 to 4.5 Gray equivalent during this initial phase. Following the prompt critical pulse, the system transitioned to a quasi-steady-state condition where nuclear chain reactions continued at lower but sustained rates. The initial energy release caused thermal expansion and convective mixing that changed the geometry and density distribution of the uranium solution, reducing neutron multiplication below the prompt critical threshold while maintaining supercritical conditions. This sustained criticality phase would continue for approximately 20 hours, producing continuous neutron and gamma radiation. The sustained criticality phase demonstrated the inadequacy of administrative controls once critical assembly formed. The ongoing nuclear chain reaction proceeded according to nuclear physics rather than facility procedures. No administrative action could terminate the chain reaction, only physical changes to the critical assembly could restore subcritical conditions. This represented a fundamental limitation of administrative control philosophy. Physical processes operate independently of procedural frameworks once critical thresholds are exceeded. The facility's radiation monitoring systems detected elevated radiation levels but could not characterize the nature or severity of the event. Area gamma monitors triggered alarms when preset radiation thresholds were exceeded, confirming that abnormal conditions existed. However, these monitors could not distinguish between static radiation sources and ongoing nuclear chain reactions, could not measure neutron radiation that comprised a significant fraction of the total dose, and provided no information about whether radiation levels were stable or increasing. The workers' immediate response reflected their training in general radiation protection rather than understanding of criticality accidents. They evacuated the immediate area around the precipitation tank when radiation alarms sounded, which was appropriate for general radiation hazards but insufficient for criticality emergencies. The workers did not understand that the alarms indicated ongoing nuclear chain reactions requiring specific intervention measures rather than simple area evacuation. The absence of criticality-specific monitoring capability created fundamental problems for emergency response decision-making. Facility personnel and emergency responders could not determine whether the radiation source was static or dynamic, whether the criticality was continuing or had terminated, whether intervention was urgently required, or whether conditions might deteriorate further. This information gap reflected the regulatory determination that criticality accidents were not credible and therefore required no specific detection capabilities. Emergency personnel who responded to initial radiation alarms faced hazards that exceeded the scope of standard radiation emergency procedures, 3 emergency workers received significant radiation doses during their response to the event, with exposures ranging up to several gray equivalent. These doses occurred because responders applied standard radiation protection approaches to a criticality accident, underestimating both the intensity of radiation fields and the unique characteristics of neutron plus gamma radiation. The continuing criticality created complex decision requirements for emergency management that had not been anticipated in facility emergency planning. Unlike static radiation sources that could be approached with appropriate protective equipment and time limitations, the critical assembly represented a dynamic hazard that could potentially increase in intensity. Emergency planners needed to assess ongoing risks, determine appropriate protective measures, and coordinate response activities while minimizing personnel exposure to unprecedented radiation fields. The physical characteristics of the sustained criticality phase reflected the complex interplay between nuclear physics and solution chemistry. Fission heating caused convective circulation that continuously redistributed uranium concentration and geometry within the precipitation tank. Steam formation and radiolysis created gas bubbles that affected neutron moderation and leakage. Chemical reactions between radiation and solution components gradually changed the chemical environment that influenced neutron physics. These physical processes operated continuously throughout the 20-hour criticality duration, creating conditions where the critical assembly was dynamically unstable but persistently supercritical. The system could not achieve stable subcritical conditions through natural feedback mechanisms because the fundamental parameters total, uranium mass, enrichment level, and vessel geometry remained unchanged. Only external intervention to modify these parameters could terminate the ongoing chain reaction. The neutron radiation component of the total dose represented a particularly hazardous aspect of criticality accidents that was not adequately addressed in facility emergency planning. Neutron radiation has different biological effectiveness than gamma radiation and requires different shielding materials for protection. Standard radiation monitoring equipment was not designed to measure neutron dose rates, and standard protective equipment provided limited effectiveness against neutron radiation. The sustained nature of the criticality event exceeded the duration assumptions underlying normal radiation emergency response procedures. Most radiation emergency scenarios assume that hazards can be controlled or eliminated within hours through standard response measures. The 20-hour duration of the JCO criticality required sustained emergency response coordination, prolonged implementation of protective measures, and extended decision-making under uncertainty about event progression. The criticality event ultimately demonstrated that nuclear safety requires recognition and respect for physical limits that cannot be exceeded regardless of administrative frameworks. The nuclear chain reaction proceeded according to fundamental physical laws once critical conditions were achieved. Administrative controls were effective in preventing critical assemblies from forming, but once those assemblies existed, only physical interventions could restore safe conditions. This represented a fundamental limitation of administrative control philosophy that had not been adequately recognized in facility design and operation. The radiation alarms that sounded throughout the JCO facility at 10:35 a.m. initiated an emergency response sequence for which neither the facility nor external authorities were adequately prepared. The regulatory determination that criticality accidents were not credible had eliminated requirements for criticality-specific monitoring, emergency planning, and response capabilities. This gap between the actual emergency and available response resources created a cascade of secondary problems that prolonged the hazard, increased radiation exposures, and demonstrated how administrative control failures could propagate beyond the immediate accident to affect broader public safety. The facility's initial emergency response reflected standard radiation protection procedures rather than criticality-specific measures. Workers evacuated the immediate area around the precipitation tank when area radiation monitors triggered alarms, assembled in designated muster areas, and initiated notification of facility management and external emergency services. These actions were appropriate for general radiation emergencies involving static sources, but did not address the dynamic nature of ongoing nuclear chain reactions, or the potential for continued or renewed criticality pulses. The critical gap in emergency response capability was the inability to determine whether the criticality was ongoing, had terminated, or might resume. The facility's radiation monitoring system consisted of area gamma monitors designed to detect elevated radiation levels from normal operations or potential contamination incidents. These monitors could confirm that radiation levels exceeded normal background, but could not distinguish between residual radiation from completed fission reactions and radiation from continuing nuclear chain reactions. This monitoring limitation created fundamental decision-making problems for emergency response coordination. Responders could not determine whether the hazard was static or dynamic, whether immediate intervention was required to prevent deterioration, whether personnel could safely approach the area for assessment or corrective action, or how long emergency conditions might persist. The absence of neutron monitoring capability was particularly problematic because neutron radiation represents a significant fraction of total dose during criticality events and indicates ongoing fission reactions. Emergency workers who responded to the initial radiation alarms encountered hazards that exceeded the scope of their training and equipment. 3 emergency responders received significant radiation doses during their initial assessment and response activities, with estimated exposures of 1 to 4.5 Gray equivalent. These doses occurred because standard radiation protection procedures were inadequate for the intense neutron and gamma radiation fields created by ongoing nuclear chain reactions in close proximity to workers. The radiation exposure of emergency responders reflected the fundamental mismatch between available response capabilities and actual event characteristics. Standard radiation emergency procedures assume well-characterized radiation sources with known dose rates and radiation types. Emergency workers typically carry gamma radiation detectors and apply time-distance shielding principles based on gamma radiation characteristics. Criticality accidents produce intense neutron radiation that requires different detection equipment, different shielding materials, and different approach strategies. External notification and communication processes proved inadequate for the complexity and duration of the emergency. JKIO's first notification to authorities occurred at 11:19 a.m., approximately 45 minutes after the initial criticality. This delay reflected uncertainty about the nature of the event rather than deliberate concealment, but it significantly complicated external emergency response coordination. Early communications did not clearly identify the event as a nuclear criticality, leading to additional delays in implementing appropriate response measures. Local emergency authorities faced unprecedented decision-making requirements without adequate technical support or established response frameworks. The Nuclear Disaster Prevention Plan in Japan did not include fuel processing facilities like JCO, creating institutional gaps in emergency response authority and coordination. Local officials needed to make immediate decisions about public protective measures without guidance from national authorities, or establish technical criteria for criticality accident response. The mayor of Tokaimura ultimately recommended evacuation of residents within 350 meters of the facility and sheltering for residents within 10 kilometers, but these decisions were made without established technical basis or coordination with national emergency planning frameworks. These protective measures proved appropriate given the event magnitude, but they were implemented based on local judgment rather than predetermined emergency response procedures or technical guidance from specialized authorities. The extended duration of the emergency response phase, lasting more than 20 hours, created coordination and resource challenges that had not been anticipated in existing emergency planning frameworks. Normal radiation emergency procedures assume that radiological hazards can be characterized and controlled within hours through standard response measures. The sustained nature of the criticality required prolonged monitoring, extended implementation of protective measures, and sustained coordination between multiple levels of government and emergency response organizations. Communication of technical information to public officials, emergency responders, and the media proved particularly challenging due to the unprecedented nature of the event in Japan. Officials needed to explain criticality physics, assess radiation exposure risks, and justify protective measure effectiveness to audiences with limited technical background. The absence of established communication frameworks for criticality accidents contributed to public confusion and complicated implementation of protective measures. Determination of appropriate protective measures required technical judgments that could not be made reliably with available information. Emergency planners needed to estimate the potential for additional criticality pulses, assess the likely duration of ongoing radiation emissions, evaluate the effectiveness of distance and shielding as protective measures, and determine whether meteorological conditions might affect radiation transport. None of these assessments could be made accurately without understanding the physics of the critical assembly and the potential for changes in its configuration. The decision to terminate the sustained criticality required technical interventions that exceeded the capabilities of standard emergency response organizations. Nuclear criticality accidents cannot be terminated through conventional emergency response measures. They require specific technical actions to modify the nuclear physics parameters that support chain reactions. The intervention strategy at JCO involved draining cooling water from jackets around the precipitation tank to eliminate neutron moderation and reflection that supported criticality. This technical intervention required coordination between facility technical staff, external nuclear physics experts, and emergency response commanders under urgent conditions with incomplete information about system status. The decision to drain cooling water was based on analysis of neutron physics rather than established emergency procedures, requiring real-time technical judgment about the most effective method for terminating ongoing nuclear chain reactions, while minimizing risks to personnel implementing the intervention. The intervention process also created new risks that had to be balanced against the ongoing hazard of continued nuclear reactions. Draining cooling water would eliminate neutron moderation that supported criticality, but personnel implementing this action would be exposed to elevated radiation fields. Additionally, there was uncertainty about whether the intervention might cause sudden changes in criticality that could endanger response personnel or create additional radiation release. Verification that the criticality had actually terminated required monitoring and analytical capabilities that were not available through normal facility operations or standard emergency response resources. Confirmation of criticality termination required neutron flux measurements, analysis of radiation decay characteristics, and assessment of fission product concentrations that exceeded the capability of area radiation monitors. External technical specialists were required to confirm that nuclear chain reactions had ceased and that conditions were stable. The coordination challenges during the extended emergency response revealed structural weaknesses in the interface between national, prefectural, and local emergency authorities. Different levels of government had different technical capabilities, legal authorities, and operational responsibilities, but no established framework existed for coordinating response to criticality accidents at fuel processing facilities. This coordination challenge was complicated by the unprecedented nature of the event and the absence of relevant experience or established procedures. Public communication during the emergency phase required balancing scientific uncertainty about radiation exposure levels and health effects with the need to provide actionable guidance to affected populations. Officials needed to recommend protective actions without definitive information about exposure levels, dose criteria specific to criticality accidents, or establish precedents for public communication strategies. The balance between providing useful guidance and avoiding public panic required judgments that exceeded the capability of standard emergency communication protocols. The decision to extend protective measures beyond the immediate vicinity of the facility required analysis of meteorological conditions, radiation transport mechanisms, and population distribution patterns that had not been included in facility emergency planning. These analyses needed to be conducted urgently with incomplete information about the radiation source characteristics, release rates, and atmospheric dispersion factors. Emergency response coordination was further complicated by media attention and political oversight that created additional requirements for public accountability and information disclosure. Emergency response commanders needed to balance technical decision-making requirements with public communication needs, legal liability considerations, and political oversight responsibilities, while maintaining focus on immediate public safety objectives. The sustained criticality ultimately required injection of boric acid solution as an additional neutron absorber to ensure permanent subcritical conditions. This final intervention demonstrated the technical complexity of criticality accident resolution and the inadequacy of standard emergency response capabilities for managing nuclear physics emergencies. The successful termination of the criticality was confirmed at 8:30 a.m. on October 1st, more than 20 hours after the initial critical assembly formation. The physical termination of the criticality at 6:15 a.m. on October 1st, followed by confirmation of stable subcritical conditions at 8:30 a.m., initiated a comprehensive investigation that would reveal the systematic nature of the organizational and regulatory failures leading to the accident. The forensic analysis demonstrated that the JCO criticality was not an aberrant event caused by individual human errors, but rather the predictable outcome of institutional design flaws that had systematically eroded safety margins while maintaining confidence in administrative control effectiveness. The investigation revealed how multiple levels of failure had combined to make a serious nuclear accident not merely possible, but structurally inevitable within the existing organizational and regulatory framework. Immediate radiological surveys conducted after criticality termination confirmed the magnitude of radiation exposure experienced by facility personnel and demonstrated the severity of unshielded critical assembly radiation fields. The 3 workers directly involved in uranium transfer operations received doses of 16 to 20 Gray equivalent, 6 to 10 Gray equivalent, and 1 to 4.5 Gray equivalent respectively. 2 workers ultimately died from acute radiation syndrome, with the most severely exposed individual dying on December 21, 1999, while the 3rd worker recovered after extensive medical treatment. These exposure levels were unprecedented in Japanese nuclear operations and represented among the highest occupational radiation doses recorded in the global nuclear industry. Emergency response and recovery personnel received radiation exposures that exceeded normal occupational limits but remained below levels associated with immediate health effects. 24 JCO workers involved in criticality termination operations received individual doses up to 48 millisieverts, while an additional 104 workers and emergency responders received doses up to 8 millisieverts. 7 non-JCO workers near the site received doses ranging from 5 to 20 millisieverts. A total of 436 persons, including local residents, received measurable radiation exposures with most individual doses below 50 millisieverts. Environmental radiological assessment confirmed that the accident was primarily an irradiation event rather than a widespread contamination incident. Atmospheric releases were limited to trace amounts of noble gases and gaseous iodine that escaped from the facility building. Environmental radiation measurements peaked at several microgray per hour at the site boundary during the active criticality phase, but decreased rapidly after nuclear chain reactions terminated. Soil, vegetation, and water samples showed minimal contamination levels that did not pose long-term environmental or public health risks. The investigation into facility management practices revealed systematic weaknesses across multiple organizational functions that had developed over several years. The 1996 procedural modification that established bucket dissolution had been approved by Manufacturing and Quality Assurance Divisions without review by the Safety Management Division, demonstrating inadequate integration of safety analysis into operational decision-making processes. This approval pattern was repeated for subsequent procedural modifications, creating a systematic gap between safety oversight and operational practice. Analysis of facility training programs revealed fundamental inadequacies in criticality safety education that left workers unable to recognize dangerous conditions or understand the physical principles underlying safety procedures. Workers received general radiation safety training and instruction in procedural compliance, but no education about criticality physics, critical mass concepts, geometry effects on neutron multiplication, or the relationship between enrichment levels and safety requirements. Training programs assumed that procedural compliance would ensure safety without requiring workers to understand the technical basis for those procedures. The training inadequacy was particularly evident in workers' inability to distinguish between safety requirements for different enrichment levels. The facility processed primarily 3 to 5% enriched uranium with only occasional campaigns, involving 18.8% enriched material, but training programs did not emphasize the fundamentally different criticality safety parameters required for these materials. Workers applied experience gained with low-enriched uranium to intermediate enriched material without understanding that critical mass thresholds, geometry requirements, and mass accumulation limits were entirely different. management oversight systems proved inadequate to detect and correct the gradual accumulation of procedural modifications that systematically reduced safety margins. Internal audits focused on compliance with documented procedures rather than evaluation of whether those procedures maintained adequate safety controls. Quality assurance programs measured consistency and efficiency of operations rather than effectiveness of safety measures. These oversight mechanisms could detect deviations from established procedures but could not evaluate whether the procedures themselves remained technically adequate. The facility's economic environment had created systematic pressures that favored operational modifications over safety conservatism. Company revenues had declined from 3.25 billion yen in 1991 to 1.72 billion yen in 1998, due to international competition, forcing repeated cost reduction initiatives and personnel reductions. Technical staff was reduced from 34 to 20 workers during this period, eliminating much of the facility's specialized criticality safety expertise precisely when economic pressures were creating incentives for procedural optimization. Examination of the regulatory oversight framework revealed several fundamental weaknesses that had enabled the accident to occur. The licensing determination that criticality accidents were not credible at the JCO facility had eliminated requirements for criticality alarm systems, specialized emergency planning, and enhanced training programs. This determination was based on confidence in administrative controls rather than systematic analysis of human performance reliability or comprehensive evaluation of potential failure modes. The absence of periodic regulatory inspections since 1992 had eliminated the primary mechanism through which regulatory authorities could have detected procedural modifications, training inadequacies, or degradation of safety oversight capabilities. Resources had been redirected to other regulatory priorities based on the assumption that fuel processing facilities presented lower risks than power reactors. This regulatory approach assumed that facility management would maintain safety standards without external verification. Investigation of the procedural modification process revealed how organizational culture and economic incentives had systematically weakened safety controls while maintaining confidence in overall safety effectiveness. The Kaizen culture of continuous improvement encouraged workers to identify and implement operational enhancements, while management incentives favored modifications that reduced costs or improved efficiency. Safety considerations were secondary to operational benefits in the evaluation and approval of proposed changes. International analysis placed the JCO accident within the broader context of global criticality accident experience. The September 30 event was the 21st criticality accident in nuclear fuel processing facilities worldwide, with previous incidents in the United States, United Kingdom, and Russia following similar patterns of administrative control degradation. 17 of the 21 accidents involved solution processing operations where administrative controls had proven inadequate to prevent critical mass accumulation. The pattern of international criticality accidents revealed common failure modes that suggested generic weaknesses in administrative control philosophy rather than problems specific to Japanese operations. Most accidents involved gradual erosion of safety practices through procedural modifications, inadequate training in criticality safety principles, economic pressures favoring efficiency over conservatism, and confidence in administrative controls that was not supported by systematic verification of their effectiveness. Economic analysis of accident consequences revealed costs that vastly exceeded the operational savings that had motivated the procedural modifications leading to the event. JCO ultimately paid more than 9.3 billion yen, approximately $93 million, in compensation to affected residents and businesses, in addition to facility closure costs, legal expenses, decontamination activities, and permanent loss of operating license. The facility never reopened, representing complete economic loss of the business enterprise. The investigation identified specific technical and organizational changes that could have prevented the accident without requiring advanced technology or extraordinary resources. A criticality accident alarm system would have provided immediate detection of ongoing nuclear chain reactions and enabled faster emergency response. Enhanced training in criticality safety principles would have equipped workers to recognize dangerous uranium accumulations and understand why established procedures were mandatory rather than merely preferred. Regular safety review of procedural modifications would have identified the safety implications of bypassing engineered safeguards like the buffer column. Specialized technical oversight of operations involving enriched uranium would have ensured that safety analyses remained current and adequate. Periodic regulatory inspection would have verified that safety programs were functioning effectively and that operational practice matched documented procedures. Organizational changes implemented after the accident addressed many of the institutional failures that had contributed to the event. Enhanced training programs provided comprehensive education about criticality physics, safety principles, and the technical basis for operating procedures. Procedural modification processes required independent safety review and regulatory approval before implementation. Management oversight systems included specific attention to criticality safety rather than focusing exclusively on radiological protection and general safety. Regulatory improvements following the accident included mandatory criticality alarm systems for facilities handling significant quantities of enriched uranium, enhanced emergency planning requirements for fuel processing operations, and more frequent inspection of criticality safety programs. International cooperation increased through information sharing about accident experience, development of improved safety guidance, and coordination of regulatory approaches to fuel cycle facility oversight. The fundamental lesson revealed by forensic analysis of the JCO accident was that nuclear safety requires more than good intentions and written procedures. Effective safety requires systematic understanding of physical principles, organizational commitment that consistently prioritizes safety over efficiency, and regulatory oversight that verifies actual practice rather than assuming compliance with documented requirements. Administrative controls can provide effective safety protection, but only when they are designed, implemented, and maintained with full recognition of human performance limitations and organizational pressures. The accident demonstrated that safety culture cannot be assumed to exist, but must be deliberately developed, systematically maintained, and continuously reinforced through training, oversight, and organizational incentives. Technical training cannot be generic but must address the specific hazards and physical principles relevant to each type of operation. Regulatory oversight cannot be episodic but must provide continuous verification that safety systems are functioning as intended, and that operational practice maintains adequate safety margins. The contradiction posed in the initial forensic question, how safety controls could guarantee the failure they were designed to prevent, was resolved through recognition that safety controls are complex systems requiring the same systematic attention to design, implementation, and maintenance that is applied to engineered safety systems. When these requirements are not met, safety controls can indeed become mechanisms through which safety is systematically degraded rather than protected. The JCO criticality accident ultimately demonstrated that administrative control systems, like any safety system, can fail catastrophically when their design assumptions are violated, their implementation is compromised, or their maintenance is neglected. The same organizational processes that were intended to ensure safety procedural flexibility, continuous improvement, cost optimization, and management efficiency became the mechanisms through which safety margins were systematically eroded until a serious accident became not just possible, but inevitable.